Alrighty. Let's see here. Do-do-do. So let's see black. There we go. Alright, we are live. Okay. Let's see. For those watching in the future, welcome back, everyone. This is... Wow. Okay, so... first stream in 2 weeks. So, let's see. Where did we... So, let's see. So we're building a balancing robot. Hello, Megan. All right. So, okay, I just started. All right. So we've been building this balancing robot. I'll just hold it for the camera here. So we got building this balancing robot. Basically, it is a robot that stands up on 2 wheels. So it's a unstable system, but it uses a control method in order to stand vertically. Basically, if it senses that it starts falling over, it will drive the other way to keep a mass balance on top of it. After the last stream, we had the ability to drive it around with a DualShock controller, and you could steer it in place, and you could also essentially control its tilt. But the problem with controlling the tilt is that if you keep it held over at a particular tilt, it will continue to accelerate until it runs out of essentially torque capability, and then it will fall over. So what we really want is, rather than controlling the tilt directly with the stick, we want the stick to control the velocity. So we want the robot to automatically set its tilt based on whether it needs to speed up or slow down. So we were trying to build that in the last video, but we did not finish. Or we're having some problems with it. So we're hopefully going to fix that today. And then we're also hopefully going to add the ability for it to stay in one place, or basically fix its rotation so it doesn't spin in a circle. It will hold which way it's pointing if you leave the controller alone, because right now it kind of drifts. So, all right, so let's see. So where did we leave off? We left off... all right, I have to zoom in here. We left off with trying to write this, what was called a velocity PID controller, or PID controller, which, rather than attempting to control... PID controller. So rather than... Oh, wow, it's just a bunch of math. Well, I mean, it is, but velocity PID controller. There we go, maybe this will be... Oh, I'm trying to find a better... Where's that graphic that I was using the other 2 weeks ago? Effectively, the velocity form of a PID controller is, rather than doing the classic setup, it tries to... the standard PID control equation is this... wow, okay. It really is just math. Okay, so that's the better way of explaining this. So basically it takes the standard PID control algorithm. It takes the current error between where you are, where you've measured that you are, and where you want to be. It takes a sum total of that error over time, or the integral of the error. And then it takes the derivative of that error function as well to see how the error is changing. And the idea is that the proportional, or the one that is directly based on the error, is some kind of response that is based on the immediate error. And then there's the integral portion, which is some kind of response based on the cumulative error. And then there is a response, the derivative portion, based on how the error is changing. So the idea of that last portion is, if the error is decreasing, decrease the response. Essentially, it's what's called a damping factor. It's if the thing you're doing is making the error decrease, and it's measuring the derivative of the error function. So if the derivative is increasing, that means you're more quickly approaching lower error, which means you should slow down how hard you're pushing it. So it's to try to limit what's called overshoot, which is you going past the point you're trying to get to, and then being in an error again, just in the opposite way. So so the velocity PID form is basically, you take the equation. So one of the classic problems with PID is that integral term. So if you have an error and the error is constant, that I term just keeps building and building and building until the system, or what's called saturated, until you basically, there's no control anymore. It's just always maxed out in one way or the other, and it can't do anything anymore. Because that I term has grown so large. So there are a couple of ways. So there are a couple of ways to try to get around that. One is called, so basically the general category of problem is called I term windup, which is the I term has gotten so big it dominates the entire equation. So the classic ways of trying to solve that is basically one is just limiting how big the I value can get. Just rather than trying to do some mathematical approach to it, it's if the I value is greater than negative plus or minus some number, then just clamp it. Don't let it exceed that number. Another way is called what's called back calculation, which is if the result of the function is greater than it's allowed to be, recalculate the I term such that the output, or such that it would fix the output of the control algorithm. And then there's also another form called velocity PID control, which is rather than dealing with this I term, what you do is you actually treat your output kind of as the integral. And you solve, rather than doing the classic P plus I plus D, what you will do instead is you then take the PID function and plug it into itself. Essentially, you solve the PID as a loop as a variable for essentially the next time step, t plus 1, and then everything that looks for t minus 1 or t plus 1 in the PID algorithm, you just replace the PID. You solve the math that way, and you end up with this much different form. And that's and it is technically solves that wind-up problem because you then just limit that output variable at how large it can be. So if you recalculate it next time, you've based on this already limited value. But the problem is there's some non-linearities. Here's a better example. The problem is that they're really hard to tune, and every variable affects all the others in ways that aren't necessarily intuitive. So it turns out a lot of people avoid them. And so I was bashing my head against a wall for a couple hours in the last stream, or like an hour or so in the last stream trying to fix this. So we're actually going to completely cut out this velocity PID control loop velocity form PID. We're trying to use a velocity form PID loop to solve our velocity control. However, what we're going to do is we are going to use the classic positional form of PID to solve velocity control because it's also perfectly suitable. We just need to basically reduce the noise coming into our function. So we used a velocity form of positional form of a PID loop to control our tilt before. And then now what we're going to do is we're going to basically copy the same logic and apply it to this velocity control. And so before we get super into this, I wanted to address an error in the code from last video, which is actually right here. So we've been calculating this timestamp delta, which is essentially how much time has passed in seconds since the previous run of this loop. And so we did this, we took the current time by getting the tick count of this task, and then we subtracted this time minus the last time we ran this loop, which is a perfectly valid way of figuring out how much time has passed, but there's a bug here. And that is that nowhere did I ever actually set this previous timestamp. So this timestamp delta just keeps growing. It keeps growing infinitely. So we actually would need to do previous timestamp equals timestamp after we calculate the delta to fix this. But one thing I did notice is that there's a little bit of, because this timestamp value is a little jittery, sometimes we'll run after 9. So the tilt sensor that we have reports its position 100 times a second. But sometimes we miss the exact 100 times. Sometimes we sample it after 11 milliseconds, and then the next time we sample it after 9. So the problem is that because this is the ticks can get off a bit. So what we're going to do is, because we know that it is supposed to be reporting 100 times a second, we're just going to set this timestamp delta just immediately to 100 times, basically 10 milliseconds, or 1 divided by 100 seconds, or 0.01. So we're just going to not worry about actually computing the previous time and deleting that previous timestamp, just to help ourselves a little bit. And another thing that we didn't do that we should do is that we actually made a little bit of a mistake in the declaration of our PID logic here. Not that it would actually cause it to be erroneous, but it makes the what's called the tuning parameters look a bit funky. So typically, what you're supposed to do when you're computing the I term of the PID controller, it's supposed to be it's the error in that time divided by the time interval, because we're essentially, I mean, it is the integral, but it is also, because it is this discrete time step, you can also think of it as a Riemann sum. And one of the things you're supposed to do when computing the Riemann sum of something is you multiply it by how much x, like the Riemann sum is if you take some function and you basically draw an infinite number of little boxes under it, to try to compute the area under the curve. You would multiply the height times how much width you sampled. And so we actually never computed the width we sampled. We just added the error to this value. So realistically, we should actually be multiplying the error times this timestamp delta. And just like with the derivative term, we should actually be, this is the slope of the error function. So because we're actually missing this time step, the value's wrong. So realistically, this should actually be divided by timestamp delta, because it's supposed to be a slope of a function. And that is going to make a big change. Because this is essentially 1 over 100, this is going to make a big change to our constants. So we now need to go back to our constants, and basically we need to we need to divide our previous Kp constant by this new timestamp delta. We need to go into our Kd constant and multiply it by the timestamp delta to basically bring it back to where bring our existing tuning values back to what they were before. So 0.025 divided by 0.01 f is actually just 2.5. You're multiplying by 100 because you're multiplying by the reciprocal, or dividing by a number that is between 0 and 1 is really, it's going to get bigger, right? So actually this 0.25 divided by 0.1 would actually be, you're dividing by 100th. Dividing by 1 over 100 is actually multiplying by 100 over 1, right? So this actually just turns into 2.5. And we need to multiply this by 1 over 100, so divide it by 100. So we end up, times 0.01 f, this is going to equal 0.011 f. So is that, move the decimal place, over 1, yeah, so that's correct. And so 1 over 5 is also just 0.2, so we'll just calculate that out, and then we'll go to our tool that sets all of our values, and let's just copy over this logic here too. So this is now 2.5, and this is now 0.011, and we'll copy it over here as well. This is 2.5, and this is 0.011. All right, cool. So we'll take that. Cool. So the next thing that we did wrong in the last video was if we looked at we had this semaphore that we use to basically, because this is a this is a multi-threaded program. We have a separate thread that is updating values that we may be in the process of using in another thread. We have this semaphore that's serving as a mutex, so that this inner piece of code cannot run at the same time. This piece of code cannot run at the same time as something else that is using this input mutex. And basically, the other place that this is used is whenever this configuration and gamepad task sets either one of the control values or the PID constant configuration. So we actually, this is mostly correct, but turns out we use these control values right here in our motor speed settings, so we actually need to move the mutex release to after we set the motor values. Or, I mean, realistically, until after we set, I mean, this is actually where we would need to, realistically where we would need to set it. Let's see, release, input mutex. Take control slash parameter lock release control. Actually, this will be release control tuning All right. So we got this. We did that. All right. So now what we're going to want to do is, since we're going to be using, since we're going to be using we already have a positional PID controller for our tilt control, our tilt angle control. We're going to be copying this, or we're going to be doing the same exact algorithm for our, our velocity control. It makes more sense to essentially break this out into a separate class or a function, so we don't duplicate the logic on accident, or not on accident. So we don't just duplicate the logic even though we don't need to. So, so the first thing that I'm going to do here is I'm going to cut, or actually, yeah, 4. We'll get there. So let's see. So what we're going to do is we're going to, you know what, let's create a new file, because this file is already several hundred lines long, which is not ideal. So we're gonna say pid.hpp, and this is going to be if indef pid hpp, define pid hpp, and if pid hpp. This means that, you know, we can't accidentally include this file more than once. Classic C++ header declaration. So we're going to do a struct PID, or we'll actually just call this positional PID, positional PID. Yeah, we'll just call it positional PID. Okay, so we'll just call it, we'll actually just say class, positional PID. And then inside here, we're going to need a KP, ki, float kd. These are our PID tuning constants that we've been using. And then in our public interface, then we're also going to need an I term to hold our windup. And then, okay, so we're going to say, we're going to take PID with no inputs, with a constructor with no inputs doesn't exist. We won't have any weird destructor stuff, so we'll just say that our destructor is default. Actually, I'm totally using the wrong class name. Positional PID. Positional PID. All right, cool. We're going to say that we can't copy this class. Positional PID. Const. Delete. This is all of our, you know, if you're a C++ programmer, this is all of your rule of 5, rule of 7 stuff where, you know, it's const PID equals delete. Let's just copy the destructor over here because separate our deleted and our defaults. Positional PID. Operator equals const positional PID equals delete. Positional PID equals positional PID equals delete. All right. So that is our normal. So we're deleting all of our implicit constructor type stuff. So positional PID. We're going to need a KP, a KI, and a KD. Actually, what we're going to do is we're going to define this class as a template, just so we can, actually, we'll just call this capital F floating. So we can use floats or doubles or whatever we want to do. All right. So this will be capital float. All right. And so what this will do, this one does, we'll do KP as KP, ki as ki, and kd as kd. All right, and then we got our constructor. There's really no thing here to do. Make sure I is 0. We have to include numeric limits here. Limits, I think, right? I think there's a new C++ numeric limits, I think, right? Yeah, numeric limits. Where is the lowest max denorm 0? Okay, well, actually. I don't think we actually need to do that. It's fine. So we'll just say this is 0. It'll cast to whatever format it needs to be. All right, and then we're gonna have a function void set constants. Set constant. We're gonna do snake case because why not? Let's do. Why not? We've been doing snake case. So set constants. Float kp, float ki, float. All right, so that's just going to be kp equals kp. ki equals ki, kd equals kd. All right, so this is just set constants. All right, and then what we're going to do is we're going to have our basically, or actually, sorry, we're going to have our float. The last thing we're going to do, float set point. And so we're going to do I, and then set point is 0. And then we're going to say float compute point process for compute, and this is going to be float. This is going to be the measured input. This is going to be oh, my print's finished. Float measured. All right, so now we can, and then actually what we're going to do here is just because we want to be able to debug some of the output, we're going to say float p, and this is going to be a pointer, equals null pointer, float I equals null pointer, float d, null pointer, all right. And then what this will do is if we come back over, and we're going to look at our existing, measured float time step. There we go. And that will come to the next line. All right. So we're going to take our response. All right. So basically, this is all we're going to need. We're going to take this, and then we're going to modify it into fitting our new thing here. All right. So we'll start by saying float error equals our measured minus our set point. Actually, one last thing, because I keep forgetting. Set point. Wow, double set squared point. All right. Set point. Float set point. Let's say set point equals set point. I don't know if that's happy or not. constants, and then float get set point. It's constant. All right. So, because I think my terms are probably all busted anyway. A control variable is our output. Our CV minus n minus 1. Whatever. Process variable, measured variable, whatever. All right. So, oh right, we need our previous error. Float. Previous error. Our previous. I gotta stick to it. Case. Actually, I don't like these capital things. Sorry, previous error. These all just are called this because they have special mathematical meaning. Set point. Previous error is also 0. Okay. So we've got float error, float time step measured, time step, set point, return, set point. Set point. Sorry. All this is fine. It's just I'm trying to be pedantic. Set point, measured minus set point. All right, float error, and then we will say you don't have to worry about this because we're never going to actually let previous error be not defined. All right, so error. So now we're going to say const float. That's going to be our capital F float. Const float. Error minus previous error. Error equals error. I times, and this is going to be our time step. All right. Float response PD. All right. So this has been our capital F float, capital F float. All right, and then response return response. And this is our output debug values, if desired. It's called back calculate. Because actually, I was looking at a paper over the term here. Sorry, I was looking at a paper. I don't think the way I'm doing this is actually correct. I think I was just limiting this at 0, but I think realistically what I'm supposed to do is just set I such that set I such that the output of the equation would be fine. But that's probably either way. So if P, which means so P here will be valid if the pointer was not null. So P equals P. If I, then it was Ki times I. Oh, interesting. I plus equals time step. Yeah, Ki plus I. Right. We're gonna. I didn't do this right. Plus equals error times time step. Ki times I. Okay. Float response I equals Ki times I. Okay. Response. I equals ED value. All right, and then we're going to return our response. All right. So update EID control variable. Okay, so I think this is correct. We'll find out. Okay, so Pico Balancer. I'm going to come back up here. We're going to say we're going to include PID.hpp down here. And instead of doing all of this stiff, we're going to say balance tilt PID state, say positional PID equal tilt PID. This is going to be KP, KI, KD. And actually what we're going to do is, now that we have this ability to set them later, what we're going to do is we're actually going to turn these into const expression, because they're never going to change. Alright, KP, KD. Alright, because they're never going to, or I should say these initial ones are never going to change. And then what we can do down here is NaN. Yeah, so we're going to delete all that eventually. So our configure, okay, actually, means we're going to actually have to move this tilt PID out of this loop. Tilt PID controller. We'll just call this tilt PID controller. KD. All right, and then tilt PID down here. Part of this is going to be tilt PID dot set constants, and then it's going to be all this stuff that we had before. KP, KI, KD. All right. Cool. Yeah, we still have the mutex, so we're good. Okay. Perfect. Perfect. All right. So now what we're gonna do is we can delete all of this stuff, Euler pitch. Sorry. Float. We're gonna say const. It'll probably infer. It might infer. Sorry. We have that. We made this a templated function, so it might infer the right type from the types we gave it here, but we'll see what happens. All right. We say const float measured rather than error. Measured equals. Let's say control. And then const float measured equals 5.f times control y. This is literally just where we're copying what came down below here, just so we can hack this up if we need to. Euler, it's actually going to be actually not measured. This is our Euler.pitch is our measured. Okay, sorry, this is actually set point. Set point 0.f, right? And then measured, it should be measured minus this thing. So measured minus control. So something minus measured, right? No, I did this backwards. Okay, so measured will be the first, and then the target will be what we want. That's how we're doing the calculation before. So actually, I did reverse this. So this is going to be set point minus measured, right? No, Euler.pitch. This is our measured minus our set point. So it's measured minus set point, which is what I had. Okay, now I did it right. Measured minus set point. Okay. Sorry. Wow. Okay. I did measured minus set point. Okay. Measured minus set point. Okay. Cool. All right. So we're going to comment these two out because that's what we were using before. And so we're going to say tilt PID dot set point. We're going to say set point. Actually, maybe we just copy this stuff in here. Set point. Control tilt PID dot set point 5.f times control. This is again just so we can turn these back on if we're experimenting. Tilt PID dot set point 0 because that's the other one we had. Okay. Update balance update tilt controller. All right. Then we can actually just skip all this stuff, and we can say const float response equals tilt PID dot compute measured. So that's going to be our Euler dot pitch. Our time step is our timestamp delta, and then we actually would like to debug this. So we're going to say float PID. It's going to be PID. Actually, this is going to be, we're going to call this tilt P, tilt I, tilt D. Tilt P, tilt I, tilt D. Just because we're just doing this because we want to be able to output them down here. So this is going to be tilt P, tilt I, tilt D. All right. Also, anybody who's watching, if you have any questions, just feel free to interrupt me. I try to read the chat, make this interactive. If there's something you want me to go over more, please just ask me. So, all right. So we can delete all of this because we're not. We moved it over to that that tilt controller class, and we're actually going to just experiment with the gamepad being the input, the way, just us controlling tilt with the controller. And Euler control is our target. Actually, so we're going to say 5.f times control I. Or actually, sorry, our target is actually going to be our tilt PID dot get set point. Nice. Let me just make sure I updated the previous everything correctly. I did. Awesome. We'll come back to see if to mess with this if we want response I. Okay. Tilt to get set point, tilt P, tilt I, tilt D. All right, does this compile even? It looks like we didn't introduce any compiler errors, so that's nice. Okay. Now does it run? That's the real question. 5.f. Control Y, gamepad. It's in our gamepad logic here. Do I stick X, stick Y? No, I feed the full stick Y into it. Okay, cool. Actually, we don't really, I'm going to say 2.5 is our maximum control angle because I'm going to crash it otherwise, right? And actually, one thing that we didn't do before that we probably should be doing is if you remember watching the other videos, when if the robot fell over, it crashed and just scuttle across the room, because there was nothing controlling the what do you call it? Sorry, there was wow. It'd be trying to pick itself back up, which wouldn't work because it doesn't have enough torque, so or traction. So it would just scuttle away. So what we're gonna do is, if the angle is too high, we're just gonna turn off the motors. So what we're gonna do here is, if the tilt is too extreme, just disable the motors. If the absolute value of Euler.pitch is greater than or equal to 45 degrees, then set motor left speed as 0, set motor right speed as 0, and then continue. Basically just skip the rest of the loop. Disable the motors and skip update. Okay. Perfect. Alrighty. This should work, hypothetically. So compile, it built. We're going to then put the batteries in the robot and upload the code and see what happens. And alrighty here. So we'll put the battery in there. Put the battery in here. I think that's actually the motor batteries. Oops. I powered the motors up first. Okay. I'm going to do that. I'm going to put in the last bat. It's going to start screaming at me. Alright. Then we're going to build. We're going to run it using our Pico Flash Project tool. Alright. Yep, and if I tilted it, just forever turns off. That doesn't seem right. Hold up. What did I do? Euler.pitch. Did I not release a lock or something? Ha ha! I didn't release a lock. That, wow, classic, classic synchronization problems. Okay, alright. Wow. This is why Sphinx is really nice. You know what we can do? We can make this real fun. We can define ourselves a little lock class. That's just extra. Of course. I'm going to define this. Sorry. Struct. Basic lock. Scoped lock. Alright. And then we're going to call ourselves a scoped lock. Let's delete. Scoped lock. So our copy constructor is also deleted. We can move constructor. Scoped lock. It's actually scoped lock. Just the one last one that's deleted. Operator equals scoped lock equals const scoped lock equals delete. We're going to say, actually this is just going to be a class. What am I even doing here? This is going to be final though. Public, say semaphore, handle t, mutex. This is already a pointer, so we're good. Scoped lock equal, what we're going to say. So scoped lock. It's going to take a semaphore, handle t, mutex, and by default it will set our internal mutex to the one we capture, and then we're going to already by default let's say semaphore x semaphore take text. Wow, alright, what the hell? Alright. Give port max delay. Okay, sorry, it's max delay. Alright, cool. And then scope block will be, which is a move constructor, is be a will be mutex equals lock. Actually, we just swap. swap self dot, no, sorry, wow, lock dot mutex and mutex. So lock mutex, and then we're going to also have a scoped lock operator equals scoped lock we're going to say swap lock. Okay, and then our special just destructor scoped lock is x if mutex x semaphore mutex. All right, so that we're just gonna cut that. We're gonna put that in a new file, utils. Yeah, there we go. Where does X semaphore take? Where do these actually get defined? That's defined in semaphore. Oh, it's defined in semaphore. Oh, we're good. Where's std swap defined though? Where is that? It's defined in utility. Wow. Oh yeah, where's this? Port max delay is undefined. Oh, tick type. Okay. Where's tick type defined? Sorry, port max delay is defined in. Might as well just include free RTOS. That'll probably fix it, right? Right? Nope. Okay. Which one of you drug this in? That's probably fine. Include. I'll call. Actually, if we're gonna rename this as RTOS utils. Nah, we'll just keep it utils. So HPP. Why not? Why not? Okay. So what we're gonna do is we're going to say scoped lock. Control lock is control lock is an input mutex, and then now, regardless, we don't have to worry about officially giving it up. It should just work, which will be cool. So we can compile that, and it doesn't compile. Oh, right, I forgot. Return pointer to this. Cool, right. Awesome. So now we can flash this. And in theory, oh, nope, wrong one. Will the row be able to balance an object placed on top of it? Almost, well, it should be able to. It's just going to be limited to based on the torque that the robot has. So let's see. If we tilt it over, it turns off. If we turn it back up, it turns back on, which means our lock's being released. Okay. So, all right. So now that that's running, let's run our gamepad tool. Gamepad. Let me turn on my little phone camera droid cam thing here. We're gonna. Nope, sorry, desk cam. Yeah, whatever. Alright, alrighty. Portable camera. And so, let me take this off the stand. So, that emergency thing we were talking about. The motors are running. If we tilt it all the way over, it turns off. So, if the robot were to fall over, it turns off. However, if we pick it back up, it balances. And you can't see it because it's so far away. But yeah, but if it were to say fall over, it's off. And if we pick it back up, it goes back up. Okay, cool. So that works. And the fact that it is balancing, it's not staying in one spot, but the fact that it is, in fact, balancing means that our PID controller is not too broken. Let's see if I can control it with my gamepad. Let me start the gamepad tool. All right, let's see when it comes up. All right, connect to the balancer. All right, let's tilt. Oh, that is really hard to control. Really hard to control. Okay. Okay, cool. Before I crash it, I'm going to do that. But if we were to crash it, it turns off, turns on, turns off, turns on, stands. Cool. Makes it so it won't run away. Let me switch back to my desktop and pull the power on the motors. All right. Desktop. Cool. Okay. Perfect. Turn off the gamepad tool. All right, our scoped lock thingy works. Our perfect. All right. Macro gamepad PID. Perfect. All right. So now what we're gonna do is we're going to start doing the. Oh, you know, I didn't even start this to see if data was coming back from the robot correctly. Hold on, let me do that real quick. All right, so start that, await. Cool. Those are okay, cool. Data's coming back. I did the PID debugging stuff. Probably works correctly. Yeah, awesome. Response. Yeah, the orientation, red, I believe, is the set point, blue is the measured, right. Okay, yeah. And then on the bottom, do I even output the response? I don't even output the response. Okay, that's a little silly of me. Okay. Oops. How about we'll fix that in the future. We'll add that in the future. Okay, now quickly, I'm gonna take a small little. That turns off my microphone. I forgot it did that. Okay. Yeah, fine. Just gonna turn off my webcam here because I'm spinning around backwards. All right. Just gonna swap. Okay, cool. All right. Now I need to review. Totally unrelated to the contents of this stream, but we're printing out some stuff for a little robot task. Print the plate in blue this time. All right, cool. All right, so next, let's see. What are we doing here? We are doing. Now we need. Okay. Yeah. Okay, straighten my back, otherwise I'm gonna hurt myself. Already hurting myself. All right. So, we are doing a thing. We are... Wow. Sorry. We're... Fabs, do the thing. Right. All right, yes. We are replacing our velocity PID controller that we were attempting to develop last time. We are going to be replacing that with a positional PID controller. The velocity controller for the velocity is going to be replaced with a positional PID controller for the velocity. Right. All right. I think the word salad out of here. All right. So, control targets. So this is the velocity PID controller. Let's say const expression float k. Velocity ki or kp equals. We'll just call this 1.0. Const expression float velocity. Fine. Velocity ai equals o dot 1 f. Actually, o dot o f. Why not? Const expression float velocity kd equals o dot f. Alright. Do a positional PD for velocity PID. Say velocity. Oh my god, sorry. Every time the state of the printer changes, it brings a little window back up, which is a little annoying, but whatever. Velocity AI, velocity KD. Alright. Perfect. So Control X is currently, or sorry, Control X is our turning right now. Control Y is our tilt target, velocity target. So what we're actually going to do, get rid of that. We're just going to base this off of a floating variable called control, right? Yeah. Control, const float control input. All right, yeah. Control. Control PID state. Perfect, perfect. Aye. And that'll let us set the set point, do our debugging. The fact that it did snake case for all the other... I'm sorry, I am... Yeah, the one thing about programming is that, you know, the style that you choose doesn't really matter, but at least you can be consistent. So, I am attempting. Aye. Alright, tilt P, tilt I. Alright, so we're gonna take, what are we gonna do? We're gonna delete all this, well, I mean, we're gonna delete control there a little bit. Previous encoder state. Alright, so now we can replace this with, we'll keep this, because that lets us get that. We'll do const float velocity, just to give us the average of the two encoder. This will give us our roughly ticks per frame. And then, right, so then what we're going to do is our velocity target minus velocity. So that's going to be our set point minus our measured, which is going to be, of course, it's backwards to the other one. I gotta stop doing that. Alright, so that means our, what did we call the velocity one? We called it velocity underscore PID. Cool. So we're gonna say velocity PID dot compute. This is going to be const float control equals velocity PID dot compute. And then measured is going to be velocity. Time step is going to be our time step delta. This is going to be our velocity. P, velocity I, velocity D. Let's put these on a new line, and those aren't even defined yet, so we're going to say float velocity F. Really, initializing things is a good thing to do, but we know for a fact that our code guarantees that the values will be set, so initializing them isn't exactly required. Let's do D. Alright, delete all this. Oh, no, not the thing we just wrote. That'd be stupid. Velocity target is our control y dot 960. So that we can actually just define 960, control I, target. Oh, I did something wrong here. Hold on. Timestamp delta. E. Where did I scale this to? Oh, hold on. Encoders. What did I do here? Lifting. Alright, sorry. Yeah, no, I did do that wrong. Alright, cool. Yay. That's funny. Alright. Okay, so velocity is this, all this crap. What we're going to do is we're going to say timestamp. Because this is velocity measured over a tiny little point in time, we got to divide this by timestamp delta. All right. Perfect. Actually, we'll just do our math here. Divide. So divide by 2.f times timestamp delta. Hooray. Math. By 2 divided by 2 would be divide by 2 squared. Right. Alright. Alright. Oh, 2.f times timestamp delta. Okay. Do all of our debuggy thing here. Velocity compute our velocity control input. And then because we had this sign flipped around, it means our control output's going to be inverted. And then our control output's going to be clamped from -1 to 1, because that's how we wrote our gamepad. So we're going to say 5.f times control. We can delete all of that stuff. Alright, so to tilt controller. If the tilt is to extreme, disable the motors and disable motors. Alright, cool. Skip update. Perfect. So our velocity is that. We're doing our... Let's put that up there. Response, do the thing. And rather than setting set point here, what we'll do is control Y. We're going to say velocity PID. Set point packet.control.y. And the set point, we're actually going to need to multiply this by some speed. So we're going to say, so this number that looks like I just pulled out of thin air, actually, is not pulled out of thin air. This number is actually, our velocity is going to be measured in encoder ticks per second. And the encoders on this robot count, we talked about it in the last video, but they count at 960 ticks per rotation. So one revolution of the wheel is 960 ticks. So 2 rotations per second, or so a 1 rotation per second is 960 ticks per second. So what we want is if we want to do 2 rotations per second, we would do double that. 960 times 2 is 1920. Control.y, and control.y from our gamepad script is going to be sent in as a value between, what do you call it? -1 and 1. So this is going to be forward and backwards. It's going to scale -1 and 1 to up to 2 rotations per second, or 120 RPM. 2 rotations per second, 120 RPM. 60 seconds in a minute. So 2 rotations per second times 60 seconds in a minute, 120 RPM. And the motors are officially capable of 300 RPM. So we don't want to exceed essentially 40% of our motors at maximum speed, because we want to have reserve torque left on. We want to have essentially reserve torque left on the table in case we need to quickly set ourselves back up. We don't. If we're already going maximum speed, we have no ability to correct, and torque falls off, as you approach your maximum RPM. So we want to make sure we have some oomph left on the table in case we get into a bad state. Wow, YouTube is really penalizing me for not streaming last week. Okay, either way, that aside, thank you all who are watching. Okay, so Control X, velocity, PID, set PID, perfect. The target is going to be velocity PID. Dot get set point. I wonder velocity error as a value in here, and I didn't have it up here. The velocity minus the target is the error. It's redundant value. Okay. I'll call it 0 for now because I'm gonna have to take it out of the thing. So okay. Set up straightening. Okay. Perfect. All right. Response. Control X. Control Y is already fed into our algorithm here. Perfect. And so, by default, if we're not feeding any input data, the velocity target should be 0. All right. So, let's compile that. See if we broke it. Nope, doesn't look like it. All right, cool. So, ideally, we're sitting in one spot now. All right, so let me plug in the programmer. And we're going to upload, compile, which we already did. We're going to our Pico tool. We're going to flash the project. I'm going to add battery back in. Oh god, that sounds horrible. Ooh, wow. I don't even want to show you guys that one. That one this is horrible. The motors are just the robot's trying to stay in one place and then it just flies off in some direction. Alright. That's just bad. I mean, hell, you can hear it. You can see it. Okay, it's just that's bad. Alright. Ugh. Alright. Alright. Well, let's not. Holy crap! Let's not do that. Oof. What else in here did I not explain? Compute velocity, response. All right, I needed to negate the output. Okay. Right, and we're doing. Actually, what am I going to call that? We're not going to let it exceed. Yeah, we're going to define, basically the logic, sorry, not 5, we're going to do 3. This is essentially the maximum allowable tilt, so we're just going to say, we won't let it tilt beyond 3. Yeah. File, flash, oh, I didn't plug in the programmer. All right. Hard to program without a programmer plugged in. All right, plug the battery back in. Ah, it's not obliterating itself anymore. It's attempting to stay in one spot. It's not doing a very good job. You know, with how well, because the problem is, all right. So here, let me switch to a what do you call it? Actually, before I do that, real quick. I'm sorry. I'm just going back and forth on you. Sorry. All right, desk cam, phone. All right, so we can see that the robot is doing this horrible thing where it's just jiggling back and forth. It's appearing to attempt to stay in one spot, but it's having a little bit of trouble. And if I push it, it tries to stop moving. Before, where if I pushed it, it would just do horrible things. I mean, you can see that it's trying to stop moving. If I push it, it tries to slow down and stop. But then it does this just back and forth and back and forth. And one thing that could be happening here is our tilt controller could be quote, too responsive, as they call it, over-tuned. Because the problem is that the robot, wow, okay. This is one of those, PIC controllers are linear control systems, and they don't really like what's called nonlinearity, which is when things aren't direct, effects that aren't a direct result of the control variable happen. So one of the things that's happening here is there's kind of some of the non-intuitiveness of the balancing robot. Oh God, yeah, is that let me hold on. What am I doing? Let me get back to my desk here. Sorry. Let me pull the motion battery out of here. Alright, sorry. So the thing about one of these balancing robots is that in order for the robot to tilt a direction, the wheel, so just think about the wheels being fixed. So if the robot tilts a direction, the wheels are rotating, right? So if you want to tilt this way in order to go forward, so you want to go, oh my God, it's hard to explain. So let's say you want to go forward. You want to go this way, right? Or you want to go a direction, you want to go this way. So the wheels, in order to go that direction, need to rotate this way, right? To go that direction. The problem is, in order for the robot to tilt that way, to go that way, the wheels actually need to rotate the opposite direction. So in order to go that way, where you want the wheel, for the wheels to be turning and going that way, in order to actually start moving, you have to lean the robot in that direction. But when you lean the robot in that direction, the wheels are actually spinning the opposite direction. In order to get the robot to lean, to start going that way, you basically have to go the wrong way just a little bit, so the robot starts following the direction you want to go, and then you can spin the motors in that direction to catch the robot essentially into the direction you want to go. So problem is that if we're trying to stay in one spot, the robot's like, hey, I need to stay over there, so I'm going to what do you call it? So the moment it starts tilting a direction to try to compensate, the motors will spin the wrong way, so it'll then immediately try to correct the other way, so it'll jiggle back and forth really bad, trying to stay in one spot, which is what we're seeing. I'm dropping things. What happened to my battery? Where'd it go? Setting things on. Oh, sometimes I don't understand how you drop something and it goes so damn far, because this is now under my shelf. I'll be right back. Okay. We got battery back. Alright. Sorry about that. Okey doke. Alright, so back to this. So what we're going to do is, for one, we might want to try reducing some of these PID constants, because it could just be responding too hard. So let's try dividing that one in half, right? Let's try adding a little bit of derivative correction here, because see what happens anyway. Actually, you know what? Before I do that, before I go and do that, let's how do I explain this? Okay. Well, actually, what we might want to do first is run. So the encoders, so I said that they rotate 960 times in one per rotation, or they ticks 960 times per rotation. Well, let's say our target speed is 960 ticks per second. Because the inertial measurement unit is reporting the tilt 100 times a second, that means that only about 10 encoder ticks can happen per run of the IMU. If we're trying to stay in one spot, obviously we're trying to keep the tick count at 0. But if you spin the wheels the other direction to try to catch your fall, it'll look like you're going the wrong way. So what we can actually do is, if we see small values on the encoders, we kind of want to try to soften the function out. So let's actually run our velocity through what's called a low-pass filter. Let's see if that helps us at all. So the way that works is that we need essentially to track our velocity. Velocity equals 0.f. Then we're going to need what's called an alpha value. So a const expression, float, velocity, alpha, which is basically your smoothing function. And I believe that, what did I do? It shows in, okay. Just look at my notes. Okay, so what we're trying to do is we're trying to smooth this out. So if we define, let's say our smoothing function is 0.025f, it means that so of the number that we're keeping track of, 0.025, 2.5% of the new value constitutes our measurement, and then the rest of it's formed of our previous measurement. So how we actually compute that is if we come in here and we say velocity at time n, our current velocity. We'll say current velocity. Actually, we keep putting all of our stuff after, so we'll say velocity current, and then actually, so we gotta break this function back up. Hold on. No, we don't actually. All right, velocity current. So we're gonna say velocity equals velocity alpha times velocity current. And then we basically add the opposite, we blend it. So plus 1 minus velocity alpha, alpha times the existing velocity. So this is a smoothing function. And so it smooths out, it's almost like a rolling average. What is the performance benefit of a const expression? So it is it's ideally nothing. It is a more aggressive dictation of the compiler that this will not change. So ideally, if you said const float something and you only ever read it, the compiler would know that can be turned into a constant. But that is essentially it's almost more explicitly constant, because technically there are things you can do with const values. Like you can actually create yourself a pointer or a writable pointer to a constant value, which is the horrific concept, but you can do it. So the real answer. So a const int takes storage in a scope. Like if in this function, for instance, if I said like const int something or const float something equals, it is technically supposed to have, well, I'm trying to remember what the spec says, but it could use, it could use state. If I then access it like as a pointer or something, it actually does have to take up storage to write that value there. the compiler won't let you touch the value. But if you use const expression, it cannot be mutated. Like it does not take it might not take storage. It is known at compile time, so the compiler is free to do whatever optimizations it can with that value. It's not this const float thingy. It doesn't actually take up space in the scope. Just using const it might. So it's a more aggressive declaration that something is in fact a constant. You can almost hand in hand think const expression. You might as well have, you could use it. You could have used a define. Like it truly is a. Well, I mean, you can take a pointer to it, but the compiler will then infer, oh, somebody took a pointer to a constant expression. Let me go. I can actually don't have to handle. I don't actually have to make it a pointer. I can go in and fill in that value if I can. Either way, all right. So we'll do, but this can't be a const expression because this is not known at compile time. Like this, there are values coming in. I am telling the compiler that I will not further change this value, but it is not a value known at compile time. Const expression must be known at compile time. And so actually one fun thing about const expression is you can actually have const expression functions, which effectively let you have the compiler do work for you. The compiler will evaluate the lot. If you have a function that returns a const expression, and it takes const expression as parameters, the compiler will actually run the function. And it will not exist in the final code, actually. You're effectively writing a program for the compiler to figure something out. So either way, there's some fun. Okay, fine. I'm on a tangent now. Okay, so if you do this horrible thing that I did a long time ago, if you look at my gist on GitHub, I think I wrote a little example where did I do this? Hold on, long time ago. Right, const expression string hash, where there's this hash function called murmur hash that basically what I did is I wrote, because also const expression, that you can't have a loop because it has to be constant. There isn't a you can't have loops because you can't have incrementing variables because it's constant. So if you use const expressions and you want to do some kind of loop, you have to use what's called tail recursion, which is essentially your index would be a parameter to the function, and you would call yourself with index plus one. The last thing you do is call yourself with index plus one. Either way, I wrote this hash function out as a bunch of tail recursion functions. And so what you could do is you could write this piece of code that says, I want the hash of some string I defined. So, does a set of all sets contain itself is the name of the string, or is the contents of the string. And I say, I want the string hash to be a compile time constant expression hash of this string. And if you actually look at the generated assembly, where is it? If you look at the generated assembly, where the hell is it? In negative something, it's in here somewhere. Yeah, so it actually computed the value of that hash, of that string, at compile time, because if you looked at the generated binary, it just contains a number. So hopefully that answers your question, Danish. You could do some horrible things with constant some horrible things with constant expression. Now, I mean, the reason that I wanted to do this was I was like, I want to be able to do a case, like a switch statement on a string, and so you could basically say, I want to switch. So switch, take a hash of this string, and then you could use compile time hash of string as your case statements, which is just, it's terrible, but whatever. That was a little. Oh yeah, that somebody's like, no, I did not intentionally have a license. Sorry for that. Yeah, that was. Yeah, so I posted. I think that back in college, right? So this was. I would say I was last active 4 months ago. Maybe on Gist. When did I push this? A long time ago, I thought. Last active 4 months ago. Yeah, over 10 years ago. Jesus. Okay, so sorry. Back on topic. All right. So where were we? Right. Low pass filter. Let's try that. Compile. Did we break anything? No. And then flash the project. All right. Things running. Sneaky close. All right. So we did that. We're gonna wake up my phone. We're gonna switch to the Droid cam. All right. Floor. And then we're gonna grab the robot. And haha, it's more. So the jitters are reduced, but I mean, the high frequency jitters are still there, but the low frequency jitters are not there. So you know what? Actually, I think what we might be able to do. What if let's detune the initial pin loop by maybe like 50%, and then add like a derivative term or something to the. Let's detune by 50% on all the pit loops, and then add like a derivative term or something. So let's do that. So we're gonna come up here. We're gonna have all of these. So say one. Oh boy. I'm gonna say rather than 2.5, let's just say 1. Let's say 1 and 1.1 and 1.0. Why not? Why not? Unscientific, but it might. Maybe it works better. Who knows? And then we're gonna say, yeah, let's have this. So we're gonna call this 0.5, and really like 0 is 0, so we don't need any integral term. I think I don't think. Just set that as 1.0. Maybe 1.5. And we don't need this control I input anymore either. Now obviously these PID terms can be kind of just magic. It's bad. Hold on, let me move this alpha value out of here. Where did I put it? Velocity alpha. I'm just gonna put this up here. Yeah, we'll just call this KA instead of alpha. KA. Constant A. Velocity KA. Okay. And then let's make sure we update in our game, since we changed our PID constants, we'll change them in here too. So, 0.1, 1.0, 0.0, yeah. Balancer, 3, velocity, alpha, okay, I think it's good. Compile, perfect. And actually, another thing I don't like. I saw on the gamepad, right? We multiplied this by 0.25. I don't really like that. Let's just make sure. Let's just have our. We can delete that too. Yeah, let's just make sure that our inputs are. What do you call it? The robot should be the thing that scales the inputs. We shouldn't pre-process the numbers. So control X. So say 0.25. Okay, cool. File. And then flash. Cool. Flashing. All right, cool. Let's see if we get our new values coming out of here. At some point. There we go. Alright, let's see what happens. Back to the droid cam. Whoa, what the heck? Happening? It is doing a wiggle. Well, that's a lot lower frequency. That's nice. It is still jiggling about. I don't like that. Well, I mean, it really help us. Alright. Well, y'all see that, right? Yeah. Jiggle, jiggle, jiggle. Yeah. What could be causing that? Hold on. You know what? What am I doing? I need to look at our data that we're collecting. Alright. So why is it doing that? One of those big pulses. Oh god, it ran away. Alright. Let's try it. Alright. Hold on. Alright. Why is it doing what it's doing? Velocity PID. Well, it is reacting very strong, like response 6,000. What the heck? What is that 6,000 value? What the? Coder ticks. Maybe I did something wrong. Hold on. Let me switch back to my desktop. So we're looking at these. Sorry. Let me rerun that just so you guys can see the way that it's moving. Just see these things. Let's go over there. Cortex. Why is that happening? Velocity PID. What's flying by? Huh. Interesting. Interesting. Okay. Well, I did. Damn it. I didn't break anything. Alright. I don't like it. Alright, so what were we seeing? We had what did we had Oh, print finished. Alright. Control. Oh, maybe I didn't do something right. Maybe this is overtuned. So we were noticing some massive spikes in the proportional error. If we were to say divide by 100, or yeah, because if you remember, look at this. Seeing massive. Is it blue's derivative, right? I think was the derivative, right? VD. Blue is the derivative term on here. So yeah, the D term is what's really throwing us off. You know, actually, let's try squishing the D term down there quite a bit. So it's just creating these massive orientation spikes. Well, let's try dividing this. Let's try dividing all these by. Let's try taking this down. Yeah, let's get rid of the derivative for now. Compile. Flash project. All right, let's try that. Let's try that this time. Well, actually, let me wait for the data to start coming onto the screen here. Switch back to that. All right. Erasing that. Yeah, there we go. All right. So, well, it's staying in one spot quite a bit now. It's still throwing well over 100. All right, you know what? It's just too much roll. What if, hypothetically, what if this control input was just too? I just don't like that. It's such a. And the funny, because yeah, if you look at the orientation target, the red line's the target. Like the controller just it's like a square wave, you know. It just the hard just I mean it's actually the position controller. Sorry, the orientation controller is actually doing a really good job there. You can see it's trying to match the red. So the red function is the set point, or at the very top under orientation. The red function is the set point. The blue is the actual angle of the robot. So the orientation controller is actually doing quite a good job. It's doing what it was told, but the velocity controller is just doing horrible things to it. Why is it setting that output point velocity 0? Like I think maybe that P term is just way too big. So we're gonna try reducing. No, it's just massive. Okay, what if we are reducing it by just factor 10? And then flash that. All right, start waiting for data to come back on our Jupyter notebooks here. Alright, well, slowly oscillating like it does before. Huh. It's still moving back and forth, and we still see that, but still get the stair step function. Huh. Why is that gain so high? What if again, like, coder ticks? We're just doing velocity as kind of our input point, so I mean, we really like. Yeah, I think we need to divide by 100 again, or divide by 10. Overall division of 100. Alright, flash. Oh, it's not plugged in. Haha. Alright, flashing. Alright. Now let's, well, okay, I will let it start spitting data back out on Jupyter Notebooks. And then... and then I'll put it on the ground. Alright. Hey, it's staying on a lot. It's not moving nearly as much. That's actually kind of funny. It's just like, look at this. It's doing a lot better job of staying in one place. It's just still oscillating a little bit. Call it. Wow. Okay, I'm so sorry. Desk cam. There we go. See, it's kind of just hovering in one spot, it's doing what it's supposed to. It's just, I really wish it wouldn't jiggle so much. So, okay, let's go back to the desktop here. So if we look at this data coming in, I think it's almost in phase with the velocity. We're not, okay, we need to measure the, what's the blue? The blue line is probably the velocity target, right? Velocity, what's velocity target? Velocity target is the red line. The velocity itself is the blue line. It's actually not that off of the set velocity. Like, I mean, why is it? Hold on, that's not right. Velocity is the measured. Velocity target is the target. Well, alright, hold on. Measured. Well, maybe it's because I flipped something. Hold on. Yeah, those are always going to be fixed because this is just literally the P term modified off of it. Okay. But we... Okay, well, we need to print, and then the error, I mean, well, the error is just going to be the opposite of this. It's just, well, our function's a lot more smoothed now. Doing a really good job holding the target pitch, but why are we instructing it to do that is the big question. Yeah, what if we just reduced this by another factor of 10? See what it does. Data to come in. All right. Well, it's doing a bit better job staying in one place. Just oscillating around a little bit, huh? All right. Yeah. Ticks velocity slowly oscillating. The orientation pit is really taking it for a loop. Oh, you know what? Dividing by... oh, God, there's that division by 0 in the I term. Okay, hold on. Instructive. Ugh. Huh. Hold on. Hmm. Well, the velocity PID response is a lot smaller. What if I turn on my controller? Can I actually drive it around now? Is that a thing? See what happens. Let me turn on the desk cam here just so you can see this horrible thing that happened. Potential crash, because that'd be funny. Haha, or not. Look at that. We can drive it around. Takes quite a bit to stop, but oh, hit the camera. Hit the camera again. All right, it's actually becoming controllable. Look at that. Rotation's not very fast, but that's fine. Doesn't stop very fast, but maybe we need to introduce some derivative term or something. I-turn? I don't know. Maybe I-turn? I'm not sure. Because I don't want to be. Why does it keep? It's funny. It does the pulsing thing that it does, where it like kind of goes forward and backward and forward and backward. Now this stair step function, not quite anyway, but yeah. Whoop. Because if we turn it around and if we go forward, we see that the target's negative. Going that way. I'm liking this velocity PID function that I see. Hold on. It's like off. You know, that technically that blending term is gonna kind of serve as an I function technically, that blend. We don't want to low pass filter the thing. Why did it spike down like that? The funny thing, wait, velocity set point. We're trying to measure the set point. Where's the velocity PID? Oh, do we ever measure the velocity target? Velocity target, yeah. We measure the set point of. Hold on. Back to the desktop. We're trying to measure the set point. Oh wait, do we not measure the velocity? Oh no, velocity target. We should be sending that with. Yeah, velocity PID gets set point. Velocity target is the red line of this graph, velocity graph here. Which, oh, well, it's only going to be scaled at, no, it should be, what the heck? Hold on. Control packet.y should be constants. I mean, I'm controlling it. Clearly something's happening. Hey, but velocity pid dot get set point. Oh yeah, there we go. Oh, it looks like the Jupyter Notebooks data is really far behind. Sorry. I think the Jupyter Notebooks data is just really far behind. So let me kill the Jupyter Notebook session here and restart it. Let's say run all cells. There we go. Velocity. Yeah, there we go. All right. Now we're measuring real data. So yeah, if we measure our velocity target, try to stop. And then the response is what's interesting is these pulses in the velocity. I wonder if that's a function of that what could that be a function of? Well, I mean, at the end of the day, this is quite drivable. This is like, this is actually really kind of starting to really work. Let me get my phone back up here. Try to bend that down. But yeah, like, this is really starting to work. Like we can rotate it. And we can drive it around. Like, it really is actually controllable. Wow, the stream is just chunky. I'm sorry. Why is this not working very well? Allow me. Desktop. Back to phone. Let's rejigger that. Yeah. No, still really chunky. I'm sorry. But yeah, like, you can see that it runs around pretty well. Like, doesn't really stay in one. I mean, staying in one place, it doesn't do very well. So let's add some derivative term here and see if that helps. See if that helps us stay in one spot a little better. So derivative, we're gonna start with on the derivative. We're gonna start with 10 times. So we're gonna start with double the p-value. We'll start with that. Plug that in. Compile, Pico, Flash. All right, I'm gonna restart this. On all cells. All right. Let's restart my gamepad script. Switch to the desk. Switch to the phone. See what happens. Well, that's not ideal. Added a derivative term and now it just jitters all over the freaking place. Oh god! Hey, our recovery, or I should say, our don't run away thing worked. Yeah, the derivative term totally just screwed over the balance of this thing. What the heck? maybe actually on the derivative term, let's divide this by 100. Yeah, let's do that. Let's see what happens. Compile. Oh, shoot, sorry. Let me switch back to my computer. Although we're soon to just switch back to the robot, right? There's the balancer. Back to balancer. Alright, let's try this. Alright, well, yeah, kind of... Oh, I need to switch back to the desk cam. Oh, hey, yeah, it does a thing. Alright. Does a thing. Well, it's doing stuff. Yeah, I know we've been talking about PID terms, but what if I wasn't making the... So I go and it doesn't like aggressively stop hard enough, right? Like maybe what could be... It's trying to stop, but it's kind of got a steady state error, kind of not really. Not commanding it to run around, but yet here it goes. Yeah, maybe I increase the P term. No, we'll just leave it on desk cam here. Yeah, we'll bring it back to the desktop. What if we up this? What if we 7.5? Triple it. Maybe we need to add some I term too. Maybe that's also another problem. There we go. Yeah, like it just doesn't want to slow down. Like, like here, hold on. The velocity target, that's, the the funny thing is, it's not when I release the stick, right? Oh, it's bouncing around. Is that like hypothetically, you know, it's you know, it should approach 0, and then oh yeah, it does spike up to up there to slow down. This should like negate, yeah, because once we hit our target speed, it does that, and then it should want to slow down. Yeah, so the pitch is doing what we want it to do. It's just not aggressive about it. It's just so what if we tripled this again, so or doubled it? So like, oh, oops, I changed the blending factor. I didn't. Oops, file. Yeah, maybe we do. Maybe we do change the freaking blending factor. Maybe leave that like that. See what happens. Who knows? Just magical values that presumably make things more stable. Yeah, like. Yeah, like, here we go. Right. There's it doing stoof, oscillating around to this point. Let me restart the controller input. Yeah, it stops a lot faster now. A little jittery, but it's controllable. Hey, it's stayed stable through that running over something. Oh. Look at that. That was actually pretty slick. Maybe I could actually let the piece on more. Yeah. What if I double it again? See what happens if I double it again. How long until we end up at a point of instability? Alright, finished. It's connecting. Controller. Oh, yeah. Oh, yeah, that's not happy. Yeah, alright, that's not good. No, it's really freaking out now. Alright. I have to up the D term to remove that instability that we just saw. Okay. Try that. Oh, that's not particularly happy looking. I have to divide by 5. Remember how these work. I had some constants I'd written down from that little demo that I'd posted as a short. And I'm trying to do the math to scale between them. Okay, hold on. I'm gonna run out of digits of precision. Alright, gamepad. Alrighty. Connected. Cool, there we go. There we go. It's working. Huzzah. All right. Well, I think that's good. I think that's working the way we want it to. Cool. I need to stop trying to drive it through the stream phone. I'm going to crash it into something. There's a bit of latency. All right. So we can drive the balancer around. It's working. So how about we add a yaw control loop now? So because one of the things it does is when it sits here, it can kind of sort of end up rotating. It doesn't rotate very fast, but it can, right? All right. Alrighty. I think this is doing good. This is doing good. Bring it over to me. I'll turn it off. And oh yeah, I've tracked so much cat hair on my desk. Right, there we go. Alrighty. Dock the robot. Turn off the motors. Bring this back to my desk. All right, put the thing back in. Perfect. Alrighty. Perfect. Stream deck back up here. Alrighty. Cool. So we've got the what do you call it? The control loop working, more or less. And we got the PID stuff isolated out, kind of. So the code's a little more straightforward on here. So let's see. Account, wait, then. Right. All right. Just trying to think. Continue. Right. Okay. Think that processes everything. Okay. So what do we do now? Let's velocity error. Right. We've been. All right. So now let's add our, no, we'll just leave that there because we defined it. Stop this. Let's now add a yaw control PID loop. Let's do that. So, yaw control, these are some funny constants. Okay. We'll say, so this is going to say yaw PID controller. And we're just going to start with, oh, actually, you know what? So we'll do ourselves another constant expression float yaw KP equals 0. We'll come in and change these. Constant expressions float yaw KI equals 0. Constant expression float yaw KD equals 0. All right. So realistically, I mean, we only technically need to have a proportional controller on the yaw, but you know, Ki can be make it converge faster. So I'm going to say positional PID, yaw PID, yaw KP, yaw KI, yaw KD. All right, and so what we'll do is we're going to need essentially track how much we want it to change, because so what we'll actually use, so okay, so what we'll do is okay, so the thing about the yaw loop is that we want to measure the amount of time that's passed since the last, or actually, wow, okay, I'm getting ahead of myself. So we're getting this input from the joystick essentially, and realistic. Hold on, all the way. Sorry, to back up a little bit. Configuration test, yeah. So this motion control packet. So right now we're just holding onto this control.x, and this is kind of like a yaw rate design, like a kind of like yaw rate. Actually, you know what? We can do it that way. Basically a rate. If we'll set, I mean, I kind of wanted to avoid these variables, but I guess we're not going to be able to avoid that. So going to say here float yaw rate point f. And that's going to be a volatile because it can change. Control Y, Control X goes away. Okay, so yaw target. I mean, we can just use the get set point function. Okay, positional yaw rate. So what we'll say, let's come down here. I'm gonna say yaw rate. We're actually just gonna define this in like degrees per second, right? So we're gonna say that a full stick is 90 degrees per second. So desired yaw is 90 degrees per second. So what we'll do here is, because we've already updated the tilt controller, update the tilt controller. Update yaw controller. And so we're going to say, so yaw rate, we're going to say yaw pid set point as yaw pid dot get set point plus yaw rate times timestamp delta, and that'll essentially our degrees per second times the amount of change that we've had in this cycle, and then add that to our current set point. So then we're going to say const float response, yaw response equals yaw pid dot compute, and we're going to get the Euler dot yaw timestamp is timestamp delta, and we'll just let it do null pointers for now on the control. And so what this is going to be plus yaw response and plus yaw response. We're going to clamp the essentially the gain of this to do not exceed 0.25. Just because we don't, we're going to say 0.5 actually. 0.25, I just don't want it to fall over, right? So times yaw response. And yaw response, okay. And so what we're going to say is that the attempted output is going to be, if we're more than 90 degrees off, we're going to say that we need a full power turn. So what we need to set KP to is, so if we're 90 degrees off, so basically 90. So if the error is 90, actually 1 over 90, 1 over 90 point f, because this will be, actually we'll just say 1 over 100, 0.01 f. This will basically stay on our proportional response. If we are 100 degrees off, multiplied by 0.1, that is a full 1.0 response. So we'll just start there. So for more than 90 degrees off, we're gonna have a full power turn. And so compile that, put that in here. I mean, I already plugged in, so Flash project. Cool. I'm gonna run our gamepad, battery back in. It spun back around. Okay, that's cool. Okay. I love robots when they do something that works. Okay, there we go. Just phone cam. Watch this. So the robot, it doesn't want to move around because obviously it's trying to lock position. But if I pick it up and I turn it, it goes back. If I pick it up and I turn it, it goes back. And it tries to stop moving. If I turn it all the way around, it spins back around. Look at that. It means if we use the gamepad, I mean, it slowly spins. Whoa, whoa, whoa. That's not what I wanted. Where is it going? It doesn't know. Oh. Haha. Yeah, the set point is, okay, yeah, that's a bug. Okay, sorry. We use the rate, right? If we exceed the maximum value that we can measure, it'll always be an error. Because the yaws are going to read negative 180 to 180, and if we exceed, 180 or negative 180, we'll never reach it, so we keep spinning around in a circle. Okay, yes, we gotta clamp. We gotta do what's called normalize. We're gonna go back to that utils thing that we wrote. We're gonna say float, or actually, sorry, template type name t normalize heading t heading. If heading greater than 180.f, then return normalize heading minus 180.f. Else if heading less than negative 180, then return and normalize heading plus, plus 360. Because degrees in heading degrees. All right, and then so we actually have to use that function, right? Okay. Normalize heading degrees. That. Okay. Oops. Oh, Jesus. Yawpid. Okay, cool. Now it should work, right? I did something wrong. Return. Oops. Normalize heading degrees. Normalize heading degrees. All right. File. Perfect. Then we go. Flash project. All right, cool. We'll switch back to the ME. Once this fires up, we'll tools gamepad. Oh. Oh, something's bad. Oh, did I do something wrong here? Normalize. Oh, I did something wrong here. Oh dear. Oh god, I forgot the exit case. Oops. Oops. Bad code. Probably blew out the stack. There we go. Now we're back. All right. Start the gamepad. Switch to desk cam. Yeah, take this off. And it's going to try to spin back around to the way that it was. When we turn it around, it'll spin back the other way. Turn it over here, it'll spin back. Turn it over here, it'll spin back. Alright, yeah, and then we got our, you can drive it around. Interesting. Wait, why did it do that? Huh. Okay, that's doing something funky. It's like there's a thing that's not working. Why does it flip and then go that way? You know, I wonder if it actually reads full on 0 to 360 instead of what I'm doing. Well, but I mean, that shouldn't matter. But the error function's not going to care. So Euler.yaw. So we'll normalize heading degrees. Euler.yaw. Oh, let me show you. Sorry. This function, we weren't gonna. We wouldn't have. Euler.yaw might not have been in the range that we wanted. So we'll do this. So we'll normalize that as well. Oops, I forgot to plug in the programmer. All right, cool. Once it wakes up a little bit, we'll restart the gamepad. Right. All right, so to balance it, let me switch to the desk cam. All right, so it's gonna try to reorient itself to the way that it was on my desk. And I'm gonna, oh well, that's weird. That's really weird. Okay, something's really not right. Huh. Hold up. Okay. That's odd. Okay, let me. Okay, we need to read out these numbers that are coming from our sensors here, because I clearly I'm doing this wrong. All right. Okay. So. Clearly I'm doing something wrong. Okay, so... Okay, well, if it says negative 180... Oh, alright, it's our math that's wrong. Right, so it's always going to do a simple subtraction. So what we really just need to do is, we can't... we need to expose our difference function to this, because it'll be like, oh, it'll be like 180 minus negative 180, which will be 0. Oh, I mean, that'd be fine. But if it was like negative 179 minus 179, And those are right next to each other in reality, but they won't be if you're doing a simple subtraction with no normalization. So that, yeah, okay. So what we need to do... Well, really what we could fix this by... well, 0, yeah, because we don't actually know which one. Okay, yeah, we need to add to our PID class a way to feed the normalization function. So what we can do here is oh god, type name, template f, okay, how do we do this? I really don't like that. I really don't like that. Actually, we'll just call this the difference function. And we'll just call this diff, and then and so typically we could say that, actually we'll say diff. Something that can do this. And we're gonna by default call this a lambda that does a minus b. Is that even legal? Oh my god, I can write lambdas as auto operators inside of... Ooh, ooh, oh, that's nasty. You can use lambdas as initializers inside a function. Oh, C++, what are you... Why? Can I actually... Will that compile? No. Oh, I will just did that wrong. Type name. Does this compile? That would be really funny. Oh, no, it doesn't compile. No matching call to positional... Float. I missed something. Differ equals... Hey. Oh, oopsie. Return. If this works, it's going to be really funny. Let me take the battery out of here. Hold on. And deduce template parameter diff equals oh dear. Oh, that worked. Oh, Jesus. Okay. Oh, baby. That really worked. Compile. Yeah, that really worked. Okay. Woohoo! Okay. And if I don't, that's the default interpretation of. Oh. So that if I. Oh, I love C++. Oh God. Okay. So because we did it that. Oh God. Because we did that, we can actually. Yeah, we can take out normalize there. And we. Oh, Jesus Christ. Oh, baby. Float. Um, float measured, float target. Normalize heading degrees measured minus target. Oh, baby. Compile. Oh, that didn't work. Oh, because I didn't return something from it. Okay. Wow. Wow. Oh, no, that didn't work either. Not deduce. And you can't deduce. Of course you can deduce. It's pretty freaking clear what it is. Oh. Yeah, but you're right. It can't. Null pointer. We gotta all of our little hacky parameters. Okay. Yeah. Now it should be able to deduce, which it doesn't. Okay. Come on. Oh, did I not save? No, I did. No response. Delta. Compute. No. Oh, I forgot to put a thing after it. Compile. It fell. Oh, Jesus. Okay. Glorious. Okay, this is gonna. If this explodes in my face, I'm gonna deserve it. Okay. And if it works, I'm a horrible person. Okay. Oh. Let me turn on the gamepad. I mean, that it. Can I turn? Oh man, it's working. Let me make my phone up. Okay. Oh, I can't believe that worked. I'm abusing C++. I'm not abusing C. I'm using C++. So we can. It's our yaw control. If I let go of the stick, immediately stops rotation. Oops. Well. There we go. So yeah, if we pick up the robot and turn it around, it'll spin back to the way that it was. And if I move my joystick stick, if I, all right. All right. Let's turn up the gain on the. Actually, we don't really need to turn up the gain. What we need to do is we need to add a bit of. Back to desktop. What we need to do is we need to add a bit more yaw. Need to add some derivative fixing. I'm going to add some KI as well. I'm going to flash the project, see what that does. All right, restart the gamepad client. All right, put this back on the desk cam. All right, 4cam, boop. It'll flip back to where it's supposed to be. And yeah. So, looks like, I need to turn up the gain, or I mean, the yaw rate, really. Because well, actually, we can evaluate how fast it spins back around. If I were to turn it 90 degrees, it snaps back pretty aggressively. So I think we just need to up our yaw rate. We're gonna do 180 degrees. We'll just double it. We'll double our yaw rate. Nope, no, I don't want to compile. Flash. Also be evil and up our maximum allowable response. Flash that. All right. All right, so we're gonna restart our gamepad client. Switch to balancer, perfect. And then, yeah, so that will restore the angle that it wants, and then we'll be able to, yeah, control it. Yep. Oops. Ah. Alrighty. So we have yaw lock too. So if we turn the robot, it stays. Bring it back over here. If we go forward and backward, it also always goes back to the yaw that it was at, which is really cool. All right, cool. I think this is working swimmingly. All right, so, and if we spin it around, it'll flip back, right? Nice. All right. Cool. Let's bring this back to the desk. Cool. So we've unplugged the motion batteries. All right. So, close my phone there. All right. So we have yaw control now, which is awesome. And all right, let's see, what time is it? It is a little short of 9:30. All right. I think that. Let's see here. Compute control input. Yeah. Compute control input. Might as well just change some of the comments here. Okay. Let's do a little bit of cleanup and set point yaw rate times 180. Let's do that. Make it a little easier to see. All right. IMU thread balancer. CY43. All right. Another fun thing we can do. We were showing off that what we did with the what do you call it? The passing this lambda here to handle the yaw. What we could do is we can also we can handle the this IRQ like that as well. Actually come down here and because one of the cool things is as long as you have a captureless lambda function in C++, you can actually cast it to a function pointer, and it'll still work because there's no state, so it has 0 size, so you don't actually need a function to hold it. So we can actually come in here and just instead of I can actually just do this. Sorry. If I could just type, that would be good. All right, yeah. So you can actually do this just fine. And no problems whatsoever. It'll compile just perfectly fine and dandy. All right. Actually, we'll just subscribe to IMU interrupt. Okay. Adderall handler. Yeah, all right, cool. The reason that you might want to do this, just to try to bring some of the functionality closer together. So like this task IMU, I mean, it's only used in these spots. Realistically, what we want to do is we don't see input mutex. I mean, input mutex is a thing. We really okay. Hold on. RTOS object, shared RTOS objects. We'll just do that. Shared RTOS objects. Do that semaphore handle, Q handle, Q handle. This will be the IMU Q, or actually that's not called the IMU Q. It's called the. It's just called the Q. It is called the. Wow, I'm blank. The Q IMU. Mutex. Input mutex, IMUQ. Really reverse the way I've been calling all these other things, right? No, this is just left, right encoder. IMUQ. Alright, well, I really ought to make sure I use consistent UQ handle, IMUQ, and then task handle. IMU task. Oh god, IMU task handle. Why not? Just to confuse everybody. This will be the IMUQ, or the input mutex. IMUQ. Configuration task. Come down, we're going to put all that up in here. I think I can do that before I start up the, anyway. This is going to be null pointer. I think it's technically valid. Not the most informed thing in the universe, but yeah, whatever. Okay. We really just want this to work. Gonna add all that. And gonna oh, it's not plugged in. Flash project. Actually, that didn't work. I broke it. Okay. That didn't work at all. We're going to need to undo all of that. Realistically, it was probably fine. It was for everything except the interrupt. I'm still trying to figure out how that damn interrupt works correctly. Alright, well, it's running now, so... what static task handles? Free RTOS static task handle. My task stack. Oh, it doesn't really work. Still need the pointer. Okay. Okay. Task handle. I don't want to do what I did here. At least in terms of creating these objects. Might not be able to run X semaphore give. That might be what's breaking things. Nope. That's doing fine. Alright. We're gonna say null footer. Honestly, IMU handle. It's fine. New task handle. Okay. So we're gonna do mutex, packet queue, don't want to deal with that. Void, did that work? Unused. Unused void param, yeah, params. Alright, cool. Okay, IMU task handle, Input actually, what's our scoped lock, input mutex. Yeah. Packet queue. Handle. Alright. File. Create this thing. Null pointer. Yeah. Alright. File, it built, flash project. Alright, still seems to work. So let's move this create task out of there down to here. Threads. All right. File. All right, flash project. All right. start the gamepad. This will be our little bitty cleanup. All right. So if we go back to the desk cam. Oh, let's see. Oh no, it's rotating. That means the yaw's not working. Or it's not seriously working anyway. Or no, it seems to be doing fine. This is also like the IMU can drift, right? So this could easily just be IMU drift error too. You know, we're checking it quite substantially, and the IMU could be thrown off the IMU, you know, because there's no compass to correct with. It's just 6-axis. So if the yaw gyro drifts any because of vibration, like we won't know. This is a rather old and, you know, unsophisticated IMU. So we can try. You know, it's like do it that way, it'll spin back around, but you know it will drift. It is an old unit. Yeah. So, all right. So I think so. Realistically, that's pretty close to feature complete on the robot. So yeah, let's do a little bit of trying to merge the. Actually, so what we'll do. Take this motion battery out. So let's merge. Let's just do a little bit of work. Merge this gamepad tool with the robot. Do a little bit of cleanup here. It's almost 10. So I guess there. So let's start by trying to merge this this gamepad tool here, set PID constants. We're actually going to add an option called. We're just going to merge these two tools. So we're going to create a new tool. We're actually going to rename set PID constants to rename this to balancer tool. Balancer host. Balancer tool. We'll just call it balancer tool. Yeah, we'll just rename it to balancer tool. Cool. And then gamepad, we'll add this stuff into the new program as well. Delete any duplicates. We'll do these duplicate. So types, motion packet, PID packet, control packet. All right. And then packet type control. Yeah, all right, cool. And then we'll copy these two functions. We'll post this into our balancer tool. All right. And then parser an argument -g for remote the -c for control, and the default is false. You know what? Let's see here. We'll keep doing this. So, gamepad main, create socket. Sock is main. Balancer, and then we're gonna send our PID configuration, mission packet, PID type config, setting configuration, which is balancer. We're gonna say control equals false. What we're going to actually do is we're going to say control equals args.control or bool args.control. All right. Control. All right, and then send bytes, and then we'll copy gamepad. So we'll say if not control, then return. Quit if we're not in RC mode. And then we'll paste our logic from our gamepad in here. All right, send all gamepad events to robot, to balancer. All right. All right. Okay. We need to flip this y value around because we just take event.value here. Oops. I want to flip the Y stick. It's going backwards. And then this is our dead zone. All right. Okay, that should work. Control pack. Oh, what? Motion packet. Oh. Hit configuration packet. Oh. Okay. Dot KP equals KP. Oh, we can do it this way. AIKD. Rather than doing it this way. Send balancing. Tilt PID loop. Pitch. Tilt PID loop. Constants. These are the ones we're using, right? Robot. And then we're using 1.1, 1 and 0.01, which is in fact 0.1, 1.0, 0.01. Yep, that's what we're using. Cool. All right. So we can do that. That'll give us a unified tool. And so we can just power our robot back up, and we can run this balancer tool. Balancer control. Oops. Oh, sorry. Tool slash balancer tool control. Oh. Oh. Control. Oh, wait. Sorry. Python arg parse. I want the presence of the argument to be the thing, not the. Okay. So it takes a value. Option that does not take a value is what I want. I just want the presence of a thing. Action store true. Ah, okay. Control. Equals store true. So then what happens if I don't place it? And it just does a thing. There we go. Alright, nice. Alright, so I'm putting on the ground. Spins around, does its little happy dance. Alright, balancer tool control. Setting constants, entering remote control mode, and in fact it does enter remote control mode. Okay. Perfect. Okay. A unified balancer client. Alright. Cool. Alright, now let's actually offer the option to set the other types of stuff, the other constants. So control packet here. I'm gonna remove velocity error from here. That'll cause an error here. And then PID utils, we're going to say PID configuration packet. What we're actually going to say is pitch PID configuration, velocity PID configuration. Actually, I take that back. We're not going to do that. We're going to modify our PID configuration to 32 underscore t. No, u int. Type. No. Why not? PID configuration packet. We're going to say PID config. We're actually going to redo this. Control state is 1, control is 2. PID configuration tilt, PID configuration velocity is 3, PID configuration yaw equals 4. Okay. Tilt velocity yaw. There we go. And then we're going to copy this, and then we're going to say yaw target, and this is YP, YI, YD. And then this big ass, so many floats. God, we have a fast microcontroller. Okay. So, oh no, my mouse just ran out of power. That's sad. Okay. Camera. Okay, so what we're gonna need to do is copy this stuff over into, actually, before we do that, balancer types. I'm going to move velocity error. Yaw target, YP, YI, YD. All floats. Do control is a type 2 packet. PID configuration is a type 3, 4, and 5 packet now. Type 3 packet, type PID configuration, velocity is 4. Type PID configuration, yaw equals 5. KD. And that matches up to what I called them in here, right? Oh, control, 3, 4, 5, yep. All right. Types. Fix that. Control, PID balancer. Down here. PID configuration. Tilt. Ace motion packet type PID configuration to velocity. Velocity dot set constants packet dot PID configuration dot KP packet dot PID configuration dot KI dot PID configuration dot KD. Perfect. Break. And then the same thing with yaw. PID. Yaw. Okay. Nice. Okie doke. Okay, then back to our balance. We'll delete the old gamepad tool because we don't need it anymore. Delete balancer tool. Actually, you know what? I'm just going to rename this a balancer client because that's really what it is. Balancer client. We're going to say Pico balancer. We just want to copy these existing constants that we have. Types. No. Client. Not actually using any of that. It's just let's say VKP equals 0.3, EKI equals 0.0, EKD equals 0.00003, YKP equals 0.02, YKI 0.001, YKD equals 0.001. Okay. 1, 0.01, 0.02, 0.003, 0, 1, 0.013. Cool. Okay. Name or flags. Ugh. And there be, can I make one that's not short? Ah, yes, in fact I can. Okay. K VKP equals 0.0013. Okay, almost there. Add argument ykp default equals 0.02. Add argument dash yki default equals 0.001. Parser dot add argument yd default equals 0.001. All right, 0.02, 0.00030, 0.0013. Okay, perfect. Okay. Ugh. All right, almost there. BKP equals float. Okay. Okay, almost there. Almost there. We're gonna say back to here. We're gonna stop this. Target, we can remove velocity error because that doesn't exist anymore. Say yaw equals 0. Yaw target equals 0. Yp equals 0. Or, oh, wait. Yp, is that already a thing? Yp, yi, yd equals 0. Okay, cool. Velocity error. It's not a thing. Okay. Equals state dot velocity. Oh no, dot yaw. Target equals state dot yaw target. Okay, state.yd. Types yd. All right, we remove the velocity error because it's not a thing anymore. Okay, I'm gonna say. Okay, now target, I think that's probably valid. Ugh. Oh, it's error. Already, oh, all right, restart. All right, All right, right, because we haven't flashed the new code yet. Okay. We need to compile Pico balancer. Upload that. All right, cool. All right, nice. Oh, we didn't even show the yaw. All right. Oops. All right. We're there. Okay. Now we're not measuring anything because in the code on the robot we did not actually write any of the yaw stuff out. Okay. Actually, we don't have to do that at all. I'm a little silly. We're already sending the yaw. So I don't actually have to do that. So we take that out, take out the yaw, because we're already sending it. Not yaw target equals yaw pid dot get set point. YP. I equals yaw I. 2 degrees. Get set point. Perfect. And realistically, we should probably just send that to the robot. Oh no, we don't. We need to delete the yaw. Okay. So we're already sending it. Which project? Let's restart code. Actually, don't have a yaw value. We're already sending it. State.pitch. State.yaw. We're already getting state.yaw, right? State.yaw. Yes, it was already there. Okay. Wow. Oh, we were just overwriting it. And then so we're gonna do that. We're gonna do that. We're gonna do that. We're gonna do that. And yaw angle. Woo. Use our controller, we can change the yaw target. Balancer client. Oh, oops. Configuration, tilt, velocity. Control. All right. So we're tuple cannot be. Oh dear. Not be interpreted as integer. What did I mess up? No. So go run. Result packet dot type. Uh-oh. Uh-oh types. Oh, oops. Did something funky. Oh yeah, now we can, oh dear. Right side, war pants, right side up or upside down? Oh, that's a good question. Cool, and if we move the joystick, we can change the pitch target, the yaw target, we can see that. Alright, awesome. So let's add the, okay, so we didn't show the, restart this. So we need to show the yaw PID graph. Alright. Alright, do that, do that, do that, do that. And it's adding stuff. Okay, it's adding. Oh, we need to. Oh, right. Stuff. All right. So we can see the loop. Let me restart that. Run all cells. So yeah, let me put the battery back in, put it on the ground. We can see the yaw gyro do its thing. Alright, so yeah, if we set the yaw target, or yaw PID, wait, I copied the wrong name, yaw PID. Run all cells. Perfect. Yeah, we can set our desired target, and the robot spins. Spikes that normalize around the thing. Yeah. Velocity PID, response. Alright. I call that working pretty freaking well. Alright. We got this unified. It's not quite unified yet. Okay, sorry. We got one last thing to do. Alter client, config tilt, right, okay. Send 2 bytes, and tilt loop constants. Send velocity, loop constants, velocity, tilt. Velocity configuration, VKP, VKI, VKD, and then we define final one for yaw. And then Y, yaw. Okay. Entering control mode. Balance of control. Alright. Oop, something went wrong. Oh. V. V. Y. 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 Alright. Alright, let me set all the constants. And that lets us enter remote control mode. Awesome. Perfect. It works. It works, it works, it works. Cool. Awesome. Alright, so you know what? Let me just, to close out the evening, we'll switch back to the phone camera. And we'll look at the balancing robot. Put the battery back in. Remote control mode, put the robot down. It's going to rotate back to the angle it was in. Alrighty. We've got this lovely controlled balance robot that goes around. It holds the target seat. I can just mash the stick forward and it just happily coasts along the ground, doing what it's supposed to do, not falling. Just push the stick and it goes around. We can set the angle. It tries to hold its orientation, minus, the gyro drifting. Got this controllable, keep saying that over and over, controllable. But that was the whole thing, is that up to this point, we've had very low control authority over it. Now it manages its own velocity. It tries to stay in one spot. I mean, it doesn't necessarily do the best job of it, but it tries to stay in one spot. And you can drive it around generally without having to worry about it falling over. So yeah, so over the last several streams, so it's taken us a while to get to this point, so over the last several streams we've been writing this control logic of this robot. So let's see, in all of this, what did we learn? So we learned how to use free RTOS on a Pico W. We learned how to connect that Pico W to the network. We learned how to send data over the network to a Jupyter Notebooks notebook to see all of the debug data coming out of the robot. So we have a live display of every control parameter. We have the ability to remote control it over the network with a gamepad. We are using multiple PID loops. We're using interrupts on the Pico. We learned how to use the IMU. We learned how to use DMA, based I2C. So, at some point I'll try to condense all of these streams down into kind of like a how-to video, because we never actually did go over the hardware of this thing. Let me switch back to my. Yeah. So we learned a lot, and this was a fun project. And in the future, we'll I guess the only major thing that we didn't get to was looking at the sub-stepping support on the quadrature encoders. So at some point, maybe I'll do another video, or I'll do another stream where we come back around and look at that. But for the most part, this balancer's feature complete. Like you keep driving around. Other than, a very explicit position lock, it doesn't, there's not really anything left. A couple things to look at in the future, I guess, would be, again, that sub-stepping quadrature encoder implementation, which would give us a lot more precise of a measurement out of the encoder rather than just, 2 ticks forward, 2 ticks backwards. It measures the time between the steps. So we could look at that. We could also look at... Actually, you know what? Before we go, before I close out, let me bring the robot back over here. There's also the what do you call it? Let me commit this code and then we'll check it out. But Yeah, we were doing that back calculation. One of the papers I read was saying that you don't want to just hold it at 0. You want to what do you call it? You want to just set the value to whatever it would take to fix the function. So we can. So let me just commit all of this. Git status, git add dot. Commit. Actually, let me just stop this. Reset notebook. Let me kill Jupyter Notebooks here so I can save it. Git add dot. Git add dot dot. Commit dash m. Feature complete balancer. Alright, it push dash u origin stream. Alright, cool. We can also do some code cleanup at some point. But okay, so now that we got this merged, let's restart Jupyter Notebooks. Jupyter Notebook. Alright, go to our tuning client. Oh, good. It didn't blow up all of my. It saved all of my notebook. Good. I'm gonna call this yaw. All right. Cool. Cool. I didn't lose anything. Whew. All right. So let's go to the PID controller. Oh, the PID controller here, and rather than doing this whole divide by ki thing here, what we need to do is if response greater than 1. What we do is we then do response, what we do is we say if I not equals 0, ki not equals 0, then what we do is I equals f minus response pd divided by ki. We just set it to that. This essentially solves the function backwards. Whatever it would take to make the output of that 1, we set I to, and divide it by ki, because we have to multiply ki by ki before we add the stuff together. So yeah, so if ki not equals 0.0f, we say I, -1, response PD, by ki. Alright. Compile that, flash that, and it might just explode in our faces because we've not been tuning it to assume that this is how it works. So this is back calculate to solve I-term windup. And we just don't want to divide by 0. Okay. So we're gonna run all cells. And do our remote control. Watch this work better. That'd be cool if it worked better, but also watch it explode. Well, let me switch to the desk cam. Okay. Oh god. No, it didn't work! Alright, it just died. Alright, Alright, Oh, wow, yeah, it's really not happening. Yep, okay. That made things worse. Okay, we'll just revert that and pretend that we didn't touch that. Alright, I had the better idea. Okay, well, we can look at why that is at some point in the future, but not today. So let's undo that. That's not a magical bullet to fix some other stuff. So, other things we can do in the future is, so this is, I mean, this is a, PID loop based, balancing system. So what we could do in the future is look at a different type of control algorithm, such as LQR, like linear quadratic regulator, or something else. Or we could look at reinforcement learning. There's a lot of fun things you can do with one of these robots. But more or less, though, it is in fact feature complete. So I've pushed all of the code. So if you want to use the code, like I totally released it under an open source license. So have fun with it. But thank you all for watching through this entire process on building this balancing robot. Next time we do a stream, we're going to be completely switching topics. We're going to be or robots anyway. So we're done with the balancer for the near future. But next time will be so if you see the big green RC car in the background there, we're going to be porting its Arduino code, its central control system uses an Arduino Uno, and there's a bunch of bandwidth issues I have with this new IMU. I'm trying to integrate onto it, but for that IMU, bandwidth issues. So I need to use a non-blocking implementation for I2C. And so I'm going to switch it from using an Arduino sketch over to using ChibiOS. And so we're going to walk through how to convert from an Arduino project or a actual robot that works. We're going to take we're going to take an existing platform that already works, and we're going to be converting it to ChibiOS and hopefully making some improvements along the way. Just starting with just a straight up conversion, a feature to feature, like the no improvements per se other than running on Chibi, and then we'll start making some changes to make it better. But other than that, and break everything in the process. Absolutely, that's exactly what we're gonna do. Danish. I'm thinking I can do a in-place conversion and slowly do features, but no, it's just gonna explode in our faces. That's how everything goes. But yeah, so that's what we're going to try to do. Learn another RTOS. We've been using free RTOS on the Pi Pico here. You can run free RTOS on the Arduino. It's just a bit heavy. So ChibiOS is a lower resource target. Although it is still used on ARM a lot. Chibi. Chibi is actually what ArduPilot uses as its underlying RTOS. So ArduPilot's built on ChibiOS, and then Pixhawk is built on, or PX4 is built on Apache NetX, which will not run on an Arduino. It's way too resource intensive. Convert to Chibi, and then we'll start working through that. Maybe we'll do some retro computing stuff at some point too. We've got a lot of projects. That time I found out my MCU has 257 halt and catch fire instructions. There are only 3 valid instructions that aren't explode, right? I think that's where we'll leave it for tonight. So thank you everyone for hanging out with me for potentially up to 4 hours. Thank you for watching this whole series on the balancer. I'll probably try to put together a compilation/simplification video where, it's not me trying to figure out everything as we go along, but everything's already solved per se. You can just follow along, and maybe that'll only be an hour rather than 20 hours of stream or however long I've streamed this balancer for. Thank you all for watching through this process, and